here we are at the end of the semester, just a little bit more to push through in the home stretch. And indeed, this is our very last night of lecture for Business Analytics 6354 and MIS 7373. So we won't be having class next week because we're going to be taking off for the Thanksgiving holiday. And then, of course, on November 30th, we'll be having our second knowledge demonstration of the semester, Exam 2, which will kind of wrap up everything for us. So this is your last opportunity to ask me questions or challenge me about whatever you would like to in real time. But of course, I will be available to you via email, for the rest of the semester. And in fact, for the rest of your life, if anything were to come up, I am here now and in the future. So with that, let's go ahead and get started. So on tonight's agenda, just a couple of pieces of administration I want to cover. And we're going to go ahead and just knock that out on our agenda slide here. So first and foremost, grades. I have been diligently trying to churn through everything, and you may have noticed that our grades for Exam Readiness Quiz 3 and 4 were just recently posted, as were your grades for Assignment 3. SQL project grades should be up this week, as will the grades for Assignment 4, which is due, well, just about 3 minutes ago. But in the meantime, so you can use Assignment 4 to prepare for Exam 2 a little bit, at 7 o'clock tonight, there is a scheduled release of the proposed solution to Assignment 4 that will be going live on Blackboard in the content section. So even though you probably won't have your graded version of Assignment 4 back for a little while, probably not in time to study it for the exam, you do have the answer to Assignment 4, so you can look at that. So I am working my way through grading. Grading is always kind of one of my, not my strongest suit, so it sometimes takes me a little bit of time, but we will we'll have grades up to date real soon now. One other thing to note, course evaluations. I don't think have received any emails or information about this yet, or maybe you have, but if you haven't, you will receive some information about that soon. But just to let you know ahead of time, course evaluations will be live on November 22nd. So 1 week from yesterday, on next Monday, course evaluations will be available. This is something that the university values, the college values, my department values, but also importantly, I value. I really like getting this feedback because I want to make sure that we are serving our students the best that we can and that everything is meeting your needs. And of course, that's the only way we grow, is to get feedback about how things are going. So if you really enjoyed the class, I would appreciate that feedback that I can pass along to Dr. Johnson and others within the college. And if you see room for improvement, let us know that too. But do be on the lookout for the course evaluation links that will be coming out probably in the next couple of days. As I mentioned just a moment ago, this is going to be our last class meeting of the semester. We will not be having class on November 23rd because that's getting into the Thanksgiving holiday time frame, and I imagine we're going to have a lot of kind of student conflicts and stuff like that, scheduling conflicts going on. So this actually, in the course schedule that I teach in the spring, there's oddly, and this is only for Tuesday night classes, as far as I can tell, actually an extra class meeting in the fall as opposed to the spring. So it kind of works out in a weird situation. But tonight does kind of wrap up all of the content that we have scheduled. So no class meeting next week. And of course, as I mentioned, final exam will be November 30th during our normal scheduled class time. So 2 weeks from tonight, we'll have 120 minutes or a 2-hour exam period starting at 6 p.m. on November 30th. So that's kind of our administrative pieces. Any questions, comments, concerns about that before we move on to other things? All right, well, hearing none, we will move on to other things. So on the rest of our agenda for tonight, we are going to take just a minute to kind of step back and look at everything that we've covered throughout this entire semester. So a little bit of a course overview and recap, kind of focusing in specifically on the things that you're going to be interested in reviewing for exam 2, and have a little bit of time to review that, ask any questions you might have. I'm happy to address, anything that you may want to ask me. And then once we're kind of wrapped up with all of our content focused on this semester and relational databases, I do want to spend just a few minutes kind of thinking about, what does the future of data management look like? And if this, has been content that you found particularly interesting, what databases and what areas of study might you want to get into next? So we'll have a little bit of time kind of looking into the future, and then a little bit of time kind of wrapping things up. Sound good? Excellent. Well, let's get started. So what did we cover in this class? BZAN 6354 and or MIS 7373, we started talking about just some basic database concepts, right? This idea of attributes that we group together to create entities, right? This idea that data is just this raw and unorganized set of values, right? That inherently it has some value kind of buried in it, but just raw data we can't get the value out of, right? We transform data into information by applying metadata, right? By putting it in context, by organizing it, by understanding what these values represent, what types of data these values are, how they're connected to one another to make up something bigger than the individual values, right? So we talked about these basic database concepts of attributes and entities and relationships and values and data types, things like that. That led into our discussion of entity relationship diagrams in our ER modeling grammar, right? And this is kind of the language, the set of symbols that we use to be able to graphically capture business requirements, right? So we could use an ER diagram to describe back to our business people how we understand their business problem and how we are proposing to create a database to meet their business needs, right? So it works in these two directions where we can use it to describe our technical understanding to less technical users, but also that we could take this ER diagram and give it to the person that's actually going to create the database and say, these are the business requirements that we are designing a database to meet, right? So our basic database concepts led into entity relationship diagrams, which eventually led into relational data modeling, which is just putting a little bit more technical specificity and a little bit more detail on our entity relationship diagrams, right? So we went from the pretty pictures with the boxes and the diamonds and all the lines and things like that to kind of a text-based representation of that we could effectively just copy and paste to create our SQL DDL or data definition language code, right? And when we start moving into this idea of relational data modeling, we started understanding some of these concepts like our cardinality of relationships and our degree of relationships a little bit differently, right? That cardinality really described the number of tuples in a relation, and our degree really represented the number of attributes in a relation, right? So we just kind of start to understand these relationships between attributes and how attributes come together to make up relations in a little bit more technically precise way. So this was the first half of the semester, and none of this will you be specifically tested on exam 2, right? We kind of have to understand this stuff in order for the stuff we've covered in the second half of the class to make sense, right? But I'm not going to specifically ask you to draw an ERD, right? Or ask you which entity the foreign key should be in or something like that, right? I'm not going to directly test you on this, but in order to write our SQL queries, right? This is one of our big topics for the second half of the semester, our structured query language, SQL or SQL. We might have to read an entity relationship diagram to kind of understand what tables we're querying, how those tables are joined together, and so forth like that. So SQL has been a big part of the second half of this course, right? We've been writing a lot of SQL queries in assignment 3 as well as in the SQL project. So I'm thinking by now this idea of select attributes from some table where some condition is equal to true should be just kind of rolling off your fingertips by now, right? So the select from where block, some of this functionality like our aggregate functions, group by, order by, having, this kind of core functionality of SQL is something that should really be getting ingrained in your brain by now. And then the other big topic in the second half of this semester has been normalization. So our first, second, third, and Boyce-Codd normal forms, using Armstrong's axioms and our inference rules to be able to identify candidate keys in a relation based on the functional dependencies that are described to us by the business, and also functional dependencies that we might infer from those semantically obvious functional dependencies. So exam 2 is really going to be this deep dive on structured query language and normalization. So much like exam 1, the general format of the exam would be that you will have about a third of your points coming from multiple choice questions, right? Because multiple choice is kind of an easy way to be able to broadly assess your knowledge on a lot of topics. So it's about a third multiple choice, about a third something that is a little bit more in-depth than multiple choice, but not like a big kind of project-oriented thing. So in that third of the exam, I might expect to show you a SQL query and you be able to tell me what the output of that would be, right? Or to show you some relations and you could tell me what normal form it's in and why it's in that normal form, something like that. So it's not multiple choice, it's like short answer type stuff. And then about a third of your grade that would come from writing SQL queries and also working through a normalization problem where you have a relation, some functional dependencies, and you have to describe or identify candidate keys, describe what normal form it's in, and then normalize it probably to third normal form. So very similar to what we did in assignment 4, but of course with the limitation that we are in a 2-hour exam block, so it has to be something that would be solvable in that kind of time frame, right? Just like when we did the ERD in exam 1, you know, I kind of made sure that it was bounded by the time that we had allocated. So that's the content for exam 2, structured query language and normalization being the focus, and that should, you know, kind of be expected, right? Makes sense? Yes.
Will the SQL we're writing, will any of it be from, like, similar to the bonus, the module 3 of the SQL project?
All right, so we have a question in the room, which is, will any of the SQL that we have to write on the exam be similar to the SQL that's been in phase 3 of the SQL project? So the SQL you have to write on the exam, it's really my goal that it would be very straightforward and unambiguous, right? And I know there has been some ambiguity and a little bit of confusion in some of the SQL project queries, right? And hopefully, while maybe frustrating, hopefully it has pushed you and stretched you a little bit further, right? Such that when you go to write these more straightforward queries on the exam, they're going to be a piece of cake, right? But when I'm looking at how I'm going to grade and evaluate things on exam, when these points really count, I want to make sure that there is no ambiguity, no lack of clarity, right? So, you know, it's going to be a situation where most likely I'll show you a screenshot of some data, right? And then probably also a screenshot of the output, kind of like on the SQL project. And you would just write, select whatever attributes from whatever tables. You might have to do some joins, group by, aggregate functions, things like that, but not something like crazy convoluted type queries. Now in the short answer based section, I might show you a hierarchical query or an analytical function with the windowing and things like that, and ask you to explain a portion of it. Something like that would be in bounds, but I'm not going to ask you to write a hierarchical query, for example. I'm not going to ask you to write an analytical function using the windowing or anything like that. Okay. Anything else? All right, so looking back, and I already mentioned this just a little bit, but looking back to the very beginning of the semester, we had this example very first night of class where we just had this wall of numbers. And what the heck does any of this mean? And of course, the answer at this point is, I don't know. I don't know what any of this means, right? I feel like there's value in here somewhere, but we can't get to it because we don't know what these numbers represent. We don't know how they're related to each other. We don't know what they're describing. But if we just put this data into context, we change it from data to information, right? So it goes from being raw, unformatted, unorganized, into organized and meaningful values, right? So data in context is information. And then ultimately, in this pursuit of data analytics and business analytics, we're going to take this information and we're going to analyze it. We're going to visualize it. We're going to do some predictive algorithms and be able to make decisions based on this information, right? So data is raw, unformatted, unorganized. Data with context has meaning. It is information. And we apply this context by having data that describes our data, also known as metadata. Okay, so this is like the data types of our attributes and the names of our attributes and the description of how individual attributes are related together to make up entities, and how entities are related together to make up, this richer set of relationships that we describe in our conceptual schema, right? So all of this is captured in our metadata. We also talked about the 4 and only 4 things we can do with data, which has this unfortunate abbreviation of CRUD, but it is to create, read, update, and delete, right? So our data definition language code, where we were creating tables, right, that is creating. When we insert data using our insert statement, that is creating data. Read, that's select. Update is update. And then delete is when we use the delete or drop commands to delete either individual tuples or entire tables, right? So every interaction we do with our data is just create, read, update, or delete. Read is what we've been doing kind of the vast majority of in this class. We also talked about this general idea of a DBMS, or database management system, and that the DBMS is this software layer that sits between the actual data and the users or the applications that want to interact with the data, okay? And we make this comparison between database management systems and just storing data in plain text files and all the benefits that the DBMS gives us, right? The benefit that this conceptual schema gives us, right? But make no mistake, when it comes right down to it, the data is still stored in files, right? Everything on your computer is a file at its very core state, right? The difference is this file and all the contents of this file is managed by the DBMS. And in order to get to the data that's stored in that file, we send the commands, or we send our requests through the DBMS, typically in the form of SQL, structured query language statements, right? So The DBMS has our data manipulation language, data definition language, and data query language functionality, all that typically wrapped up in SQL, structured query language. Also has utilities for managing security of the data, managing users, doing backups and recoveries and running reports, things like that, all built into the DBMS. Of course, the DBMS that we've been working with in this class is Oracle. A couple of other very popular DBMSs, Microsoft SQL Server and MySQL. So these are two pricey commercial options. MySQL is a very popular open source database management system, which actually, as of, well, I don't know, maybe 10 years ago now, was purchased by Oracle. So this is kind of a child here. PostgreSQL is another open source relational database management system that we talk about in Business Analytics 6356, kind of the part 2 of this class, right? So these are a couple of examples of database management systems. We talked about the 3-tier schema architecture. We have our internal schema, which is the kind of nuts and bolts, like how the data is actually divided amongst the hard disks and the database servers and things like that. Internal schema depends on the underlying hardware architecture. Our conceptual schema, this is where we've spent the vast majority of our time talking about in this class, but this is where we define our attributes and our data types of the attributes and what attributes make up entities and how entities are related to one another. So that's all housed in the conceptual schema. And then the external schema, these are the views of our data that are catered to individual users or applications. And in the external schema, these views show users or applications exactly what they need to see, nothing more, nothing less, which increases the simplicity and the security of interacting with our database, right? It's simpler because in the external schema, we've already, in this view in the external schema, we've defined if we're joining 5 tables together, we're defining that in the external schema. So when a user accesses this, they just query this one view in the schema instead of having to worry about all these views, right? Or all the joins that we might have to do. Also more secure because we're not exposing any data that the user or the application doesn't need access to. Models. A simplified expression of an observed or unobservable reality used to perceive relationships in the outside world. And Dr. George Box here, who had this great quote, all models are wrong, but some are useful, right? They're all wrong because they are a simplified expression, right? We're not getting all the details, right? But some are useful, and they are useful because they are simplified expressions, right? They're smaller. They're focused in on just exactly what is important and interesting to the business, right? The university has a data model or has a model of you guys as students, right? Includes your PeopleSoft ID, your first name, your last name, your email address, your phone number, your mailing address, right? These are the things that the university needs to know about you. Very useful. Not a perfect representation of you. It is wrong, right? But it's wrong in all the right ways. The model is perfectly correct. It'd just be the real thing, be so complex, generally speaking, that it wouldn't even be as useful for that business case, right? And the other nice thing here, we can model not only something we can observe like a student, but we can model these unobservable realities like a Business Analytics 6354, which isn't a tangible thing that exists in the real world, but it's still something we're interested in a business, for our business case, right? Because you students enroll in this kind of imaginary idea of a course. You pay to be enrolled in this course, which doesn't really exist. But hopefully it's useful. So speaking of models, I think this is the first model that we actually created in this class, right? Or we talked about a dog grooming salon where dogs are owned by customers and groomed by employees who work at locations. This ER model has entities which we represented by these boxes, relationships which are diamonds between the boxes. We have all kinds of different attributes kind of hanging off of these entities, and as we found out later, even sometimes hanging off of our relationships, which are captured in our gerunds. And then our ER modeling grammar lets us document different constraints on our attributes, right? Whether they're required or whether they're optional, whether they have to be unique, if they have multiple values perhaps. Also our cardinality and participation, so describing some characteristics of the relationships between attributes. So our ER modeling grammar is how we were able to precisely capture all these business rules to describe back to the business and to describe to our more technical people who are actually going to implement the databases, which might be you guys. Oh, and we created this big ol' ER diagram describing Bearcat. I think that was our 5th night of class, maybe. Good times. So speaking of the attribute or the characteristics of our relationship, cardinality, we talked about 4 different types of cardinality, one-to-many and many-to-one, which are basically the same thing, just working in the 2 directions. So, you know, we have one coach coaches many players, but a player has just one coach, right? That's our one-to-many or many-to-one relationship. We have a many-to-many relationship where many people shop at a store and a store, or many people shop at a store, but a person shops at many stores, right? Many to many, which is just made up of 2 one-to-many relationships. And recall that when we modeled these many-to-many relationships, or when we started creating the tables to capture this, we actually decomposed the many-to-many relationship into 2 one-to-many relationships and created a special entity called the gerund. Yes. So many-to-many decomposes into 2 one-to-many relationships using a gerund. And then finally, we have our one-to-one relationship where there's, you know, exactly one instance of each entity participating in the relationship. This moved us into our discussion of the relational data model with Dr. Ted Codd here, who was the father of relational database management systems, created in 1970 while he was working at IBM. And when we moved from our conceptual modeling into relational modeling, right, we kind of got some different definitions around cardinality and around and degrees of a relation. We said a database is a collection of relation. A relation is a 2-dimensional table made up of rows and columns. Our rows are tuples, our attributes are columns, and then every attribute has a domain of possible values of the attribute. We described how we can create relationships between relations by applying our foreign key constraint. And our foreign key constraint says that all values of an attribute that is a foreign key must be in the domain of values of the candidate key to which it refers, right? So for our foreign key attribute, the set of possible atomic values of that attribute or its domain is the domain of values of the candidate key that it refers to, right? This is where this all starts kind of coming together in a technical way. So we introduced this idea of all of these different types of keys. So super keys, any combination of attributes that can uniquely identify every tuple in a relation. And we talked about characteristics of a relation, and one of the characteristics of a relation is that every tuple has to be unique. We can't have any duplicate tuples in a relation, so because of that, we know we always have at least one super key that is just every attribute in the relation, right? And likely, there's going to be many superkeys in your relation, right? Many combinations of attributes that can uniquely identify every tuple. But what's more useful than that is a candidate key. And a candidate key is unique and irreducible. So a superkey that we can no longer remove any attributes from and it remain unique is a candidate key. Okay? Candidate keys are made up of key attributes. So a key attribute is any proper subset of a candidate key. A non-key attribute is any attribute that is not a subset of a candidate key. Okay, so these are attributes that don't play any role in uniquely identifying tuples in the relation. Primary key is just one of the candidate keys that we have blessed as the primary key by applying the entity integrity constraint, which just means that we can't have any null values for the attributes that make up the primary key. And then alternate keys, any candidate key that we did not select as our primary key. We also, before exam 1, introduced our relational algebra operations. We had 2 unary operators, meaning that they execute on just one relation, project and select. Project, which returns a subset of attributes that we're interested in, and then select, which returns a subset of tuples that match some criteria that we specify with a Boolean expression. So project and select are unary operators. Then we have a whole bunch of binary operators, including our 3 set theory operators of union, intersection, and difference. And in order to use any of our set theory operators, we have to be union compatible, meaning the 2 relations that you're interacting with have the same number of attributes and the pairs of attributes are in the same domain. We also talked about a Cartesian product, which is every possible combination of tuples from the 2 relations that we are interacting with. Cartesian product in and of itself, not super useful, but what we did find to be useful is if we created the Cartesian product and then selected from that resulting relation only the tuples where some Boolean expression evaluates to true, right? Where we have some matching value between the 2 relations that we brought together in the Cartesian product, which is really the equivalent of doing an inner join, right? So to do the Cartesian product and then look for some condition of equality between 2 attributes, 2 or more attributes, very similar to doing an inner join operation, or specifically our equijoin. Okay, so that's going to return any tuples that have a matching tuple in the other relation based on the value of the attributes that you specify in your joining condition. And then we also talked about our outer joins, a left, right, or full outer join, which will return all tuples from one relation or the other or both relations, regardless of if they have a matching tuple in the other relation. So an outer join is going to give us everything our inner join gave us, and then whatever tuples didn't match from one relation or the other relation or both, depending on if it's left, right, or full. Yeah. So set theory, we already kind of talked about this a little bit. Our union intersection difference, union being kind of equivalent to or, right? You're in one set or the other. Intersection being kind of similar to and, you're in set A and set B, so it's this overlap here in the Venn diagram. And difference being similar to the not operation, right? So the difference of Houston minus UH is you're from Houston, but you don't attend the University of Houston. Or UH minus Houston being you attend the University of Houston, but you're not from Houston, right? So it's cutting out the overlap here. We already talked a little bit about decomposing our many-to-many relationships using the gerund. And this is a great example of why we kind of changed our definition of degree when we moved into relational modeling. So we went from conceptual to relational modeling. One of the things that we had to change was to stop using many-to-many relationships, decompose them into one-to-many relationships, and that's when we started understanding the degree of what we had originally said the degree of a relationship is how many entities are participating in that relationship. And we said the degree of a relation is how many attributes it has. And we kind of illustrate this by saying, well, a gerund that's decomposing a relationship between two entities is going to have two attributes, right? And that's why the degree of a relation is the number of attributes in the relation, while the degree of a relationship is the number of entities participating in that relationship. So we use the gerund to decompose our many-to-many relationships. And we kind of have this stepping stone from our relational model, which goes from, again, our graphical illustration of our understanding of the business case and how we're going to solve this, or how we're going to create this in a database, going from our graphical illustration to our more textual illustration. And I described that when we get to this point, we can just almost copy and paste our relational model to create our DDL, right? Because here we have the name of the relation, which is going to ultimately be the table, and then the names of all of our attributes, right? So if we just put create table in front of this, and then add the data types of our attributes and comma delimit that, we basically have our DDL here, right? And then we add in some additional constraints, saying what attribute is going to be our primary key, if we have any domain constraints about the values of the attributes, and so forth like that. And ultimately, we should be getting to a place, hopefully we're in a place, that we would be comfortable kind of moving back and forth between DDL and an ERD, right? And each one of these create table statements is representing one of the boxes in our ERD, right? So create table instructors with all these attributes is creating this, create table courses, create table sections, create table students, create table enrollment, and then the magic is happening right here. So when we created this sections table, these lines here that define our foreign key constraint, this is saying students, one of the attributes in this relation is a foreign key that references this attribute in, what's it? Oh, sorry, this is the sections relation. There we go. One of the attributes in this relation is a foreign key that references an attribute in the instructors table, right? So this line right here is representing this diamond on our ERD. And then this line, that this attribute in the sections relation or sections table is a foreign key that references an attribute in the courses table. This line is creating or is representing this diamond on our ERD, right? Same thing here in our enrollment table. We have two relationships between enrollment and students and enrollment and sections, right? So hopefully, we all feel like we could look at an ERD like this and generate this data definition language code, or we could look at DDL like this and draw an ERD that looks like this. So that's what we did up to exam 1. And since then, we've gotten deep into structured query language and normalization. So the basic SQL, the stuff that I expect you to come out of this class and just be able to do without looking up anything, without thinking too hard about it, is the basic, select from where block. Select some attributes or asterisk for all attributes from some table or multiple tables if we're doing a join, and then optionally where some criteria is true. And I say optionally, but most of your SQL queries are going to have some conditional statement here. So select from where. If we're doing our where evaluation with some kind of fuzzier search, we want to use wildcards instead of equality or greater than or less than. We're going to use the like operator. Order by, if we want to change the order that the rows or the tuples are returned in. Group by, which is of course useful for our aggregate functions or aggregate queries. So if we want to find the average of some value or the count of the number of rows that are returned, the minimum, the maximum, those are our aggregate queries, and they go with, or almost always are going to have a group by included with them. And then if we want to make any kind of comparison based on the result of one of our aggregate queries, we use the having command, which is very similar to where, except it's working with the output of something like average, min, max, sum, or count. And then we also talked about some string manipulation functions that I think come in super handy. Substring, in-string, length, our concatenation, where we just had the two vertical bars or pipes that we use to bring together strings of text. So these are all of our kind of single table functions. And then to bring two tables together, we talked about using the Cartesian product, using the inner join operation, or our left, right, or full outer joins, our set theory operators, and doing subqueries, which is where we have a full SQL statement inside another SQL statement. And our subquery is going to generally execute first and then return some values to the outer query that it's going to use to complete the execution. So these are the ways that we can interact with two tables at a time. And if we're bringing together 3 or more tables, we call these binary operators because it's always just 2 at a time. So if we're doing 3 or 4 or 5 or however many tables, it's always handling them 2 at a time. So we're going to join 2 tables together, which is going to create, or 2 relations together to create another relation, which that third relation will be joined to. And then the fourth relation is joined to the output of that, and so on. Right? That understanding doesn't really change the way you write your SQL, but that's what's happening, right? It's always 2 at a time, and it just kind of builds on each other. So for the exam, this is what you should really be focusing on being able to write for your SQL statements. We also talked about some more advanced, I don't know if I would even classify this as advanced, but maybe kind of more nuanced SQL, or a SQL that is not as commonly used, but is going to be very helpful in kind of some, in particular cases, right? This stuff used all the time, right? If you're doing this on a daily basis, you're using all of this stuff on a daily basis. This stuff may be a little bit fringier, right? Like our decode and case statements, which allowed us to look at the value of an attribute and then do something based on what that value is, right? Decode, letting us take a value like FR and replace it with freshman, and SO and replace it with sophomore. Or if you just had like 1, 2, 3, 4, and 5 representing freshman, sophomore, junior, senior, graduate, you could say, hey, when you see a 1, return the word freshman instead, right? That's what decode does. Case gives us a little bit more flexibility to say, if value equals 1, then return this, or do this, right? And if value equals 2, do this other thing, else do this other thing, right? So case gives us a little bit more flexibility with our if-then structures. Hierarchical queries, where we have these unary relationships where a table or a relation is in a relationship with itself. The examples we had in class were like on an org chart, right, where you have employees managing other employees. That's when we wrote our hierarchical queries. We also talked about some things that kind of extend the functionality of our group by function. Cube, which gave us not only the results of the groups, but then the result that we would have gotten if we hadn't had the group by at all, right? Kind of the overall results. Roll up, which gives us every possible combination of groupings. And then grouping sets, which is grouping sets was the indicator of whether the result came from the group by or the cube or the roll up, right? So some extensions to group by that kind of, I think, give some minor advantages above and beyond what we get from group by that might come in handy. I want you to know that that tool is there in your arsenal. We talked about ranking, so rank and dense rank, your window functions, your model clause. So look at all this stuff. I might show you some SQL using this and ask you to explain what a portion of it is doing or what it would do if we made some changes to it. But I'm not going to ask you to write SQL queries that incorporate this, okay? You might have to read SQL queries that use this, but I wouldn't ask you to write SQL queries that use this. Make sense? Yeah, look at this. This is what I just said, and it's documented forever, eternally, in your notes, in the slides that are posted to PowerPoint, or posted to Blackboard. Excellent. So the other big topic from the second half of the semester has been normalization, right? This idea of functional dependencies and attributes that determine the value of other attributes. So we capture all of our functional dependencies, which are really technical representations of our business rules, in these dependency diagrams where we drew out all of our attributes and then had arrows pointing from the determinant to the dependent. So functional dependencies, dependency diagrams, how we interact with our functional dependencies using Armstrong's axioms and our inference rules, which are just kind of extensions of the three axioms, to identify candidate keys using either the synthesis or decomposition method. So we identify our candidate keys, and based on that, we can determine if a relation is in first, second, third, or Boyce-Codd normal form. And then we need to be able to normalize up to third normal form. I probably won't throw a normalized to BCNF thing at you. I just think third normal form is a pretty good place to land for most of our business problems. So this is a dependency diagram. As we've described a couple of times, our functional dependencies can be semantically obvious, meaning that they were explicitly stated to us by the business, right? Something like, all of our employees have an employee ID, and we can look up their first name, last name, and address based on that employee ID, right? Or functional dependencies can be inferred by taking, whatever functional dependencies we know and combining them together using Armstrong's axioms to come up with new functional dependencies, right? So a semantically obvious functional dependency might be, we can look up the department an employee is part of based on their employee ID, right? And then another semantically obvious functional dependency would be, we can look up the manager of a department based on the name of the department, right? If you tell me it's the accounting department, I can tell you the manager of the accounting department because that's the department head is functionally determined by department name. So based on those two semantically obvious functional dependencies, we could infer a functional dependency of, if we know an employee's employee ID, we can determine the name of their manager. Because employee ID determines department, and department determines department head. So therefore, employee ID also functionally determines department head through the property of, starts with a T, transitivity, yeah. So that's our transitivity axiom. A determines B, and B determines C, thus A functionally determines C. And we can say an attribute in a relation functionally determines some other attribute if for a value of that original attribute, so A functionally determines B, if for a value of A there is one single specific value of B, right? And just because A functionally determines B, there is no reason to believe that that B would functionally determine A, right? PeopleSoft ID functionally determines your first name. You give me a PeopleSoft ID, there is only one value of first name that's going to correspond to that PeopleSoft ID, right? But if you give me a first name, Alex, there's probably 500 PeopleSoft IDs that would correspond to that first name, right? So B doesn't determine A just because A determines B. Determinant functionally determines your dependent. And anytime we have undesirable functional dependencies, and that's when the determinant is not a candidate key in the relation, that is what is going to lead to data redundancy and ultimately modification anomalies. And we had examples in class of where data redundancy leads to problems with inserting data, updating data, and deleting data. Yeah, so those are our modification anomalies. If we have undesirable functional dependencies, we can't just get rid of them, but we can resolve the problem through this process of normalization, right? And through normalization, our undesirable functional dependencies can become okay and desirable functional dependencies. We move those undesirable functional dependencies and their attributes out to a new relation where the determinant is a candidate key, and we leave behind the determinant in the source relation so that the determinant in the new relation can refer back to, or I'm sorry, the determinant we left behind in the source relation can refer to the determinant in the new relation as a foreign key. Okay, we'll have an example of that in just a moment. But of course, Armstrong's axioms, the three primary, reflexivity, augmentation, and transitivity. Reflexivity is this idea of trivial dependencies, doesn't tell us anything new, and basically just says a determinant can functionally determine any subset of itself, right? Which also means all attributes functionally determine themselves. If I know your PeopleSoft ID, I can use that to figure out your PeopleSoft ID. That's what reflexivity says. Also, if I know your PeopleSoft ID first name and last name, I can use that to figure out your first name, right? Any subset of the determinant. Augmentation says we can add anything at all to the determinant and it will still determine the dependent, or we can add the same thing to both the determinant and the dependent. Okay, so if X determines Y, then it's also true that X and any other attributes will still determine Y. If your PeopleSoft ID determines your email address, your PeopleSoft ID and your first name, last name, and hair color will functionally determine your email address, right? Kind of like this idea of a super key. Super key is just a candidate key that we've added some extra junk to. Doesn't change the fact that the candidate key is still able to uniquely identify. Or we can add the same thing to both sides, which is really just kind of like reflexivity, right? If X determines Y, then XZ determines YZ because Z determines Z, right? This also is very similar to our composition rule, right? Because think if we had two different functional dependencies here, X determines Y and Z determines Z, we're just kind of stacking those on top of each other, and that's composition, right? These inference rules are really just implementations of our axioms. And then transitivity, we already talked about this one. This is how we can bridge two functional dependencies where we have an overlap between our dependent and determinant. So if X determines Y and Y determines Z, then it's also true that X determines Z. If employee ID determines department and department determines department head, then it's also true that employee ID determines department head. Union just says if a determinant determines two dependents independently, then it also determines those dependents together. If x determines y and x determines z, then it's also true that x determines yz together. Decomposition, just the other side of that. If a determinant determines two attributes together, then that determinant also determines those two attributes separately. If PeopleSoft ID determines first name and last name, then it's also true that PeopleSoft ID determines first name and PeopleSoft ID determines last name. You don't have to get them at the same time. Composition lets us stack two functional dependencies on top of each other. If A determines B and C determines D, then it's also true that AC determines BD. And then my favorite one to say and my favorite one to do, I think it's a lot of fun, pseudo-transitivity is just like transitivity, except we're just looking at one of the attributes in the determinant in the other functional dependency. So in this case, if x determines y and yw determines z, since x determines y, anywhere we have a y, we could put an x. So it would also be true that xw functionally determines z. So that's pseudo-transitivity. You guys probably got a lot of practice with this in assignment 4. And all of the worked examples we had in class previously. And based on our identification of candidate keys, based on our functional dependencies and using Armstrong's axioms, we were able to assess the normal form that a relation is in. So if we are talking about some set of attributes as being a relation at all, if we're calling something a relation, and if it is in a database, it is at least in first normal form, okay? If you meet the requirements to be a relation, you don't have multi-value attributes, all of your attributes are atomic, we're in first normal form. Second normal form means you are at least in first normal form, but also have no partial dependencies. So we don't have any non-key attributes that are functionally determined by just part of a candidate key, okay? And this is kind of simplified definitions. The full definitions, of course, are in the slides we previously had. Third normal form means you are in second normal form, so no partial dependencies. And also you have no transitive dependencies, which means we have no non-key attributes functionally determining other non-key attributes. And then finally, BCNF says that every determinant, Boyce-Codd normal form, every determinant must be a superkey. And what this ultimately winds up doing is fixing this situation. So third normal form says no non-key attributes functionally determining other non-key attributes. But it would be possible, and you would be in third normal form, for a non-key attribute to functionally determine a key attribute, right? Because then that non-key attribute, or that, where we have a key attribute functionally determining another key attribute, and that would not be considered a transitive dependency, okay? So Boyce-Codd normal form violations, you have to have at least two candidate keys that are composite and that have one or more overlapping attributes, okay? So when we get to BCNF, we get rid of this possibility of having a non-super key functionally determining any key attributes. So all of our determinants in BCNF are definitely going to be superkeys. So this is the, I think we have this example in a previous slide, but this is just kind of the simplest, most straightforward, all-inclusive example that I can come up with that illustrates a violation of second and third normal form. So in this case, we have these three functional dependencies. Here's our dependency diagram. A and B together functionally determines C. B by itself functionally determines D. And C by itself functionally determines E. So we could identify our candidate key either through synthesis or decomposition. But in this case, we may be able just to look at this and kind of divine the candidate key, right? Because A and B functionally determine, or AB together functionally determines A and B through reflexivity. A and B functionally determine C because of functional dependency 1. B functionally determines D, so if we know A and B, then we know B, and B functionally determines D. So AB functionally determines A, B, C, and D, and since A and B functionally determines C through transitivity, since C determines E, then AB also determines E. So in this case, we have a candidate key of AB, and we are currently in first normal form. And why are we in first normal form? Which functional dependency is causing that?
Number 2.
Yeah, functional dependency 2 is our violation of second normal form because we have a non-key attribute which is being functionally determined by a part of this candidate key. So this is a partial dependency. So in order to get rid of that, we're going to move this functional dependency 2B determines D out to another relation. We're going to create a new relation or a new table in our database with these two attributes, but we're going to leave behind this determinant B in this source relation, and this is now going to be a foreign key that refers to B in the new relation. Okay, so it's going to look like this. So here's our new relation with this functional dependency B determines D. Now this B attribute is a foreign key that refers to this attribute and could be used to join these two relations back together. So at this point, relation 2 is in third normal form, right? Because B is a candidate key because it is unique and irreducible. No partial dependencies, no transitive dependencies. We are in third normal form. In relation 1, still AB is our candidate key. AB functionally determines C is fine, but C functionally determines E. This is a non-key attribute functionally determining another non-key attribute. That's a transitive dependency, violation of third normal form. So R1 is in second normal form right now. So in order to resolve that, we're going to move C determines E out to a new relation, leaving behind C. So now this is a foreign key that refers to this candidate key. This is a foreign key that refers to this candidate key. And now R1, R2, and R3 are all in third normal form. Yippee. It's a good place to be. And yeah, here's our description about the foreign keys and the relationships, right? So we could write SQL to join this back together, right? We could say select asterisk from R1, inner join R2 on R1.B equals R2.B, inner join R3 on R1.C equals R3.C, right? So we do one join to bring these two together, and then we do a join to bring this into the fold too, right? So this is just breaking that one big messy table with all these undesirable functional dependencies. This is going to have data redundancy problems into 3 tables, which we can then join back together with our foreign key. Excellent. All right, so that's a recap of our entire semester in about an hour and 5 minutes. So that's either a lot of content that was crammed into like 65 minutes or maybe 65 minutes worth of content that was just spread out over 13 weeks. I don't know which direction you want to think about it in, but this is what I hope you guys are going to be taking out of this class. So we had a few questions peppered in already, but any other questions that we want to address? So now that we've kind of wrapped up our discussion around SQL and relational databases and how important and awesome data is kind of in the modern world, you might be kind of wondering, what's next in the world of data management? Like, we've mastered SQL and relational databases. Have we mastered everything we need to know for working with data, right? And it's maybe kind of a yes and no type situation, right? Because relational databases are a very important part of data management and of business analytics and of just everything we're doing in the world today. And they've been around forever, right? Forever, for 50 years, right? Forever in computing timelines. And that really kind of speaks to how rock solid the relational data model is, right? Because it's been, it was developed in the 70s, and the, mid 80s is when we really saw businesses adopting databases kind of at scale. And we saw a massive amount of development in the relational data space in the, mid 80s up through the late 90s and even throughout today. But the core ideas that relational databases are built on are really kind of the core ideas that Ed Codd suggested way back in the early 70s. So kind of a really interesting situation. So very important all these years later, still very widely used, and you'll find a little bit of debate about the future of relational databases online. And but I'm pretty firmly in the position that I think they're going to be around and in very heavy use for the foreseeable future, right? Probably for the span of your careers, this idea of relational databases and SQL is going to be something that's important and really, really serve you well. So, and even if not, this provides a great foundation for all of the other database things that are kind of up and coming and emerging technologies. But the thing that kind of has changed or shifted the world around data management is this idea of web scale data. So back in the 70s and 80s and even the 90s, like we just used data in a completely different way, right? And it was not on anyone's radar. You couldn't have even predicted this concept that we would have millions and tens and hundreds of million people spread all across the world accessing the same data, and not even just reading the data, but reading and also writing to the data, right? And this is just not what relational databases were designed to do, right? The whole idea of relational database management systems kind of hinges on this idea that we've got this central repository of data, and all of the users and applications that are connecting to this database are kind of in the same general physical location, and that we're looking at dozens or maybe a few hundred users or applications that are interacting with this data, right? So it was more built for housing data within a company, and that's what it was used for many years. But now in this kind of modern world of having Facebook and Twitter and TikTok and Google Maps and YouTube and Netflix and all of these data-driven applications that have users all over the world, well, one of the things we have to consider is that if we have users in North America and Europe and China and Australia, right, we're spread all over the world, it takes a long time for data to get from a data center that is in Houston, Texas, to a user who is somewhere in Europe, right? And by long time, like in computing terms, I mean like a half a second, right? That's a long time for a computer. A half second is a long time. And maybe a half second doesn't seem like much, but if you've got an application that is making, dozens of database queries for every operation that it does, well, those half seconds start adding up,
right? And when you've got dependencies within the application, like a half second of latency can make something virtually unusable, right? So the solution to this, right, would be to get the data closer to the users, right? So you've got now data centers and servers hosting this data in your application in, several cities in the US and in Europe and across Asia and Australia and kind of all over the place. So you spread or you distribute your application out around the world, but then you get into problems of data integrity, right? Because if you've got, say, two database servers, one that's in North America and one that's in Europe, and we said that it takes a half second or a second to get data between these two locations, well, now your data is always going to be at least a little bit out of sync, right? Out of sync by however long it takes to copy that data. And from an operational point of view, like it's probably not actually feasible when you've got a lot of data changing in both places to keep those databases in lockstep sync. Okay, so you just kind of have this inbuilt problem of data integrity, right? And so relational databases just don't really work to scale out, right? And to deal with having tens or hundreds of million users connecting and reading and writing and all of these kind of unknown data structures, right? So what we've been seeing in the data management space over the past 15 years or so is this idea of non-relational database management systems, okay? And a lot of the rules and a lot of the framework around non-relational database management systems kind of flies in the face of a lot of what we've discussed in this course about relational database management systems and integrity constraints and relationships and foreign keys and not having data redundancy and things like that. It's a very different paradigm. So if this is something you're interested in, and I've had a few advertisements for my other class a few times throughout the semester, but you might want to check out Business Analytics 6356, where we go into more depth of all of these topics. And I know several of you have already signed up for it, so I look forward to seeing you again, hopefully face-to-face next semester. But we'll be talking about another relational database, PostgreSQL, which is in this relational database space, along with Oracle, which we talked about, of course, in this class. So we'll be looking at some kind of additional relational database functionality. We'll talk about the other four current genres of database management systems: the column family database, two document databases, MongoDB and CouchDB, a really interesting type of database known as the graph database. We'll be looking at Neo4j, and then key value databases, in particular Redis and Amazon's DynamoDB. Okay, so a lot of these ideas of, we have something we're interested in and it's made up of a collection of attributes, right? This idea is kind of pervasive across all data management, right? But everything else is kind of up for grabs when we start looking at these other types of database management systems. So some of them, or really just one of them in this case, is still row oriented, right? So we kind of still think of it as a collection of attributes making up a row, and that's our column family database of HBase. But then we kind of dispense with this idea of these row-based tables with the others. In document databases, we think of data as being collections of documents. And in a collection of documents, every document can have completely different sets of attributes, right? Whereas in a relational database, what we've been looking at this semester, every single row in our table is going to have the exact same attributes, right? And we defined that in our schema, right? The schema defines the collection of attributes and their data types that make up a table, but by and large, these non-relational databases don't have a schema that defines what the data looks like, which gives us a lot of flexibility in being able to define what our data looks like even as we're writing it into the database. We get a lot of flexibility on the front end, but we pay for that by having not as much flexibility, generally speaking, on the back end when we're trying to query the data, right? And one of the neat ways that this difference in mindset is described is that in a relational database, we know what our data looks like ahead of time, but we don't necessarily know what questions we want to answer with our data. Okay? We know what the data looks like ahead of time. That's defining our schema, but we don't know what questions we want to ask. And as we've seen when we're writing our SQL code, we can use SQL to ask and answer almost any question about this data because we've defined ahead of time what it looks like. Whereas with these non-relational databases, we flip that saying and we say, we know what questions we want to ask ahead of time, but we don't know what our data is going to look like, right? We don't define a schema. We enable data that has whatever attributes to be written into our database. But in order to get that kind of flexibility, we have to really be careful about how we design the queries that we're going to be asking. We need to know that ahead of time. Okay, so a very different way of thinking about data management. But we replace the idea of rows with documents, or with nodes in a graph, or with items in a key value data store. And we generally don't have this idea of joining different pieces of data together, with the exception of our graph databases, which are all about joins and do joins and complex relationships even better than a relational database. But these are the kind of emerging technologies that enable us to get around the shortcomings of relational databases that don't let it scale up and scale out to deal with web scale data. Okay, so it's a different way of thinking about data management, but I think it's interesting. We do a lot of very hands-on stuff in the class, and we also talk about a variety of cloud-related topics because just by the nature of the beast, these distributed databases are often kind of tightly integrated with other cloud computing topics. So, if you're digging this data management stuff, check out BZAN 6356. I think it'll be face-to-face, and it will be actually in this same time slot. It will be Monday night from 6 to 9. So that's next semester for some of you, or some semester in the future, whatever. But as far as this semester goes, I always like to wrap up by just kind of thinking about, did we actually accomplish what we set out to accomplish, right? And if we look at the very first page of the syllabus where you have the course description and learning objectives, which this kind of sets out what we're going to be doing, the course description says, among other things, in this course, we'll learn about the fundamentals of data modeling, database design, and structured query language. By the end of class, you should have a solid understanding of how and why businesses use databases and the tools necessary to start designing, developing, and using databases yourself. And I feel like you guys have done this. I hope you feel comfortable enough to say that you would be able to design, develop, and use a database yourself. Right? We've read business requirements and created ERDs and took those ERDs and created relational schemas and DDL code that goes along with it. And we've written a lot of SQL codes to query our SQL queries to query our data. Right? So I think we did a good job there. And then the specific learning objectives here were that we would be able to describe the differences between data, information, and metadata. And we started with that on the very first day of the course, that data is this raw, unstructured, not really useful in its current state. And then we apply metadata to give the data some context and some meaning, and it becomes this useful information. We created a data dictionary in our very first assignment. We created entity relationship diagrams throughout the whole first half of the course in assignment 2, in our Bearcat story, and in multiple other examples. Similarly, we created relational data models all through the first half of the course and in these assignments. To infer and describe the types of data structures the system is using, that was in assignment 1, assignment 2, in the Bearcat, and in various other assignments and examples throughout the course. First, second, and third normal form, all in the second half of course, and of course a key component of assignment 4, and then composing SQL code to create, read, update, and delete data and data structures. Again, kind of the crux of the second half of course, assignment 3 of the SQL project, and even at the end of the first half of the course, just before assignment or exam 1, right, was writing our data definition language code. So I hope you all will agree that we made it through our learning objectives and kind of what we hope to get out of the course. And I hope you all feel like you got a lot of useful information out of the course, because that is kind of the goal here.
So as far as logistics of the exam, again, this will be 2 weeks from tonight, Tuesday, November 30th, during our normal class time on Blackboard, very much like how we did exam 1. So we'll have 2 hours starting at 6 p.m. and closing up at 8 p.m. I will be on the Zoom meeting just in case you have any technical problems. However, you do not have to join the Zoom meeting. Just go to Blackboard and do the exam, and you're kind of on your own there. And again, it will be approximately 1/3 each of multiple choice, some type of short answer, fill in the blank, matching, something like that, and then 1/3 of writing SQL queries and doing normalization. And then that will wrap us up for the semester. No final exam during exam week. How are we feeling? Feeling good? All right, well, with that wraps us up for the semester. So hopefully you guys found value in this. Hopefully you can go out and do some great things in your job, in your life, and whatever personal projects you're working on. We, as I mentioned, won't be having any class next week because of the Thanksgiving holiday. If you need anything between now and then, course related, send me an email. Happy to do that. If I can help you in any way, even far beyond this course, if you get in your job and you're like, I don't know how to do this thing, feel free to reach out to me. If you have success stories, feel free to let me know. If there's any way I can ever help you, feel free to let me know, because I'm here for you now. I'm here for you in the future. You guys have a great rest of your evening. Be safe getting home, and we'll see you when we see you.